This advanced higher biology video is going to talk about liquids, solutions, and ultimately two types of dilution. Now, when it comes to liquids, we need to handle liquids and transfer volumes of liquids in varying degrees of accuracy. And these are the four main ways in which we would measure and transfer liquid from one container to the next. We have a measuring cylinder, which is by far the least accurate, but the easiest one to use. We then have the most accurate one, which is called an autopipette, which is used for delivering really small volumes of liquid. A syringe, which is not very accurate when it comes to measuring, but is really efficient and quick when it comes to distributing or dispensing the liquid out as needed. And the final one there represents a burette, which is used in a particular type of experiment called a titration and is very accurate. So the autopipette is really exclusively used in biology. It is used for delivering very small but accurate volumes of liquid. You can, on the side of it, there is a number display which you can rotate, which allows you to change the volume that it can dispense. There's a plunger at the top, so a plunger at the top here, that has two sort of stops. So when you push it down, you can feel one stop, but you can go beyond that and you can feel a second stop. When you want to take liquid out of a container, the first thing you do is push the top down to the first stop. You then put the tip of the autopipette, the bit at the bottom, you put that in your solution, and then you slowly let go of the pressure at the top, and it will suck up the specific quantity volume of liquid that you wanted. When you want to distribute the liquid, you would then push both stoppers down and it would get rid of all the liquid. And the second stop is basically an extra volume of air that allows you to push everything out of the tip. The burette is another accurate way of delivering volumes, and it's mostly used for dispensing. It's not used for measuring things in. Before you use it, you need to rinse the burette with whatever solution you're going to be dispensing from it. And then there is a tap at the bottom here at the side, which is what you turn and it opens up and the liquid comes out of the bottom. Okay, you fill from the top, but the liquid comes out the bottom. And you can see there's a scale down the side, which actually goes from 0 to whatever number is there, usually 50 or 20, so that you can record how much liquid you have dispensed into your container. Usually you start at the 0 value. You don't have to, you just have to make sure that you record whatever volume liquid level is at the start, and then you let it run down until you've dispensed however much you need. Okay, now whenever you're looking at a burette, you can see that there is a curve on this liquid. Now that curve is called the meniscus, and meniscus with the C there. And you can see it's got a top part and it's got a bottom part. You want to read it from where the bottom of that curve touches the scale, not the top. Okay, so you can see that on this one, the precise value is 20, because remember you're counting downwards. So 19.1, 2, 3, 4, 5, it's sitting on the 20 line, always measuring from the bottom of the curve. These are used in titrations, which is a technique you don't specifically have to know for advanced higher biology, but one that you may find yourself using during your project. The bulk of this video is going to talk about dilution. There are two types of dilution, and each one has a calculation associated with it. So, serial dilutions are important. Dilution involves reducing the concentration. Now, the reason why in biology you would look at diluting a solution is because whenever you make up a solution, there's always error associated with it. You might have weighed out something incorrectly. You might have transferred something incorrectly. If you make a concentrated solution with error in it, every time you dilute it down by adding in water, you're actually diluting your error and you're making your concentrations more accurate. And so it is a way of minimizing error, as well as allowing you to take one concentrated solution and produce many different concentrations of diluted solutions from it. Now, if you repeatedly dilute a stock solution, and a stock solution or a standard solution is one in which you know the concentration accurately, when you're doing that, this is called serial dilution. And serial dilution can be done. So the first one is a linear dilution. And this is where you have one solution and you put a bit of that solution into every other solution that you're starting with. So this is our 1M glucose solution. And you can see that in the first one, we've added 1 centimeter cubed. The second one, 2 centimeter cubed, 3 centimeter cubed, 4 centimeter cubed, 5 centimeter cubed. But what we've also done is add water. 9, 8, 7, 6, 5. And what this means is that the more of your stock solution that you've added, the more concentrated the tube will be. So the final tube on the right-hand side is the most concentrated because it's got the most of your stock solution. What you need to do is always decide on a final volume for your solutions. And you can see for all of these, when you add them up together, that adds up to 10, that adds up to 10, that adds up to 10, 10, and 10. Now there is an equation for what we can do to work out the volume of stock solution needed in order to produce a solution of a particular concentration. Now the equation we're going to use is C1 V1 equals C2 V2. Now C1 is your stock concentration, V1 is your volume of stock solution that you would need. C2 is your final concentration, and V2 is your final volume. So what you're usually trying to work out is how much volume of stock solution are you going to use. So I'm going to take an example of this tube here. C1 V1 equals C2 V2. Our concentration is 1. So 1 multiplied by whatever volume we need is equal to, well, we're making a 0.4 and our volume here is 10. So 1 multiplied by V1 is going to be 4. So our volume 1 is 4. And you can see that's what we added. So we can always use that. It is usually working out what volume of stock solution you're going to need. Sometimes it might be working out what the final concentration is, but one thing we always need to be cautious of is what is our total final volume. That's something that we always need to work out. So here is an example question. So what we want to do is we want 35 milligrams per centimeter cubed. That is our concentration 2. This is our stock solution, that's concentration 1. What we want is C1 V1 equals C2 V2. First thing we need to do is go through all of our options and find out what would the final final volume be. Well, 21 is the total of those. So our volume 2 would be 21. For this one, it would be 200. And for this one, it would be 480. So what we need to do is look at concentration 1. So 700 multiplied by V1 is going to be 35 multiplied by V2. And what we need to do is just work out which one of these fits into that. This is our stock solution. So these are all our V1s. These are all of our V2s. So if we look at option A, if we look at option A, we would say 700 times 1, does it equal 35 times 21? If we do that in our calculator, 35 times 21 is 735. So 700 and 735, those are not equal. Let's try B. What we would do is 700 multiplied by 10, it should equal 35 C2 multiplied by 200. Now 700 times 10 is 7,000. 35 times 200 is also 7,000. So that is our correct option. Now this next one, what we've got, again, identify our stock solution, so that is our concentration 1. We want our concentration 2 to be 32. We have got 2 volumes. These would be volume 1, how much stock solution. Our final volume, V2, is the sum of both of those. So we've got 520, we've got 750, and we have got 300. So in each case, what we're doing is 800 times V1, does it equal 32 multiplied by V2? So let's look at A. We would have 800 multiplied by 20. Does that equal 520 multiplied by 32? Well, 800 multiplied by 20 is 16,000. 520 multiplied by 32 is 16,640. So no. Our next one, option B. 800 multiplied by 30. Does that equal 750 multiplied by 32? 800 multiplied by 30 is 24,000. 750 multiplied by 32 is 24,000. So it looks like that one is correct. So if you try this one at home and see which one of those A, B, or C that you get, remember, work out your C1, your C2, those are the numbers at the top. V1 is going to be your volume of hydrochloric acid. V2 is going to be the sum of both the volumes. Hopefully, if you've had time to do that, pause the video if you don't. You should find out that it is option C. Now here is a hard example from a past paper. Now again, we have 2 different solutions that we have got that we are putting together. We have got our inhibitor volume and our buffer. Our buffer is what's being used to dilute it. Remember, a buffer solution is a solution that resists the addition of acid or alkali and will retain its pH. Normally, instead of water, you would be using buffer solutions. Now what we want is our final solution, the concentration of the stock solution is 80%. So that means that C1 is 80%. We want 20% as our C2. So we can just ignore the symbols and just use 80 and 20 as our values. We also, in this, we want a final volume of 25. So that is our V2. We need to work out V1, and V1 is going to be our inhibitor. So the first thing we need to do is check which ones of these options actually will give us a final volume of 25. Now the reason why this is a hard question is because our final volume also includes those two things. So our final volume has 1 centimetre of glucose and 5 centimetres cubed of FBS. Then we've got everything else. So that gives us 25 minus 6 is 19. So our total volume of inhibitor and buffer has to be 19. And we can see that from experiment 1, where the total of the buffer and the inhibitor was 19. This will allow us to eliminate some of the options because the volume is too high. 4.75 plus 20.25 adds up to 25, which is too high because we've already got 6 centimetres cubed accounted for. Also, 6.25 plus 18.75, that also adds up to 25, which is too much. So we can eliminate those. All we need to do now is do our calculation, C1V1 equals C2V2, to see out of B and D which one is our correct answer. So if we look at B, concentration 1 is 80, volume 1 is 4.75, concentration 2 should be 20, and volume is 25. So we just need to check, do those numbers equal each other? So 80 multiplied by 4.75 is 380. I do not think that 20 multiplied by 25 equals 380. Nope, it equals 500. And I do not know why I needed to use a calculator for that. So this means that hopefully, whenever we do option D, C1V1 equals C2V2, 80 multiplied by 6.25 equals 20 multiplied by 12.75. So 80 multiplied by 6.25 is 500. 20 multiplied by 12.75. 80 multiplied by 6.25 is 500. Oh no, sorry. I got V2 wrong here. V2 is 25 because it is not this number. It is this number. 20 multiplied by 25 is 500. That is my fault. Sorry. So that is your correct answer there. Okay, that is a hard multiple choice question. Always check for your final volume if anything else is being added to make up that final volume, not just your stock solution and water or buffer if you're diluting it. Right, our second type of dilution is called a log dilution, And in a log dilution, we start with one stock solution. But what we do is we dilute it to make a new solution, and then we dilute again and again and again. So what we're doing is each solution is going to be usually 10 times less concentrated than the one before it. And the one thing that's being missed is that we're taking 1 centimetre and we're adding it to 9 of water in each time. To make sure that every one of these has the exact same volume as each other. Okay? So whenever we take 1 centimetre cubed and add it to 9 centimetre cubed of water, we are diluting it 10 times. And so we would get an equivalent of 10 to the minus 1, or we're dividing by 10. Okay? If we then take our 10 to the minus 1 and we do the dilution, we are again dividing it by 10 once more to get 10 to the minus 2. So 1, 0.1, 0.01, so on. Each time we do it, we are usually multiplying by 10. Dividing by 10. However, we have to carefully always check the volume going in and the total volume in the tube, because sometimes we're not doing a 10-fold dilution, sometimes we're doing a 10 or 1,000 dilution. Now, these dilutions are mainly used in microbiology because you would have cultured your cells in a culture medium with serum, with growth factors, your vitamins, your nutrients in there, and trying to grow a large number of cells. However, when you want to count the cells, you need to dilute that cell culture until you've got a countable number. Usually, what you're looking for is being able to see anywhere between 30 and 300 cells when you're looking and counting the solution by doing dilution. So this is how a dilution would work. You would take your dilution, your original solution or inoculum, which is your first sample, dilute it, have it on a plate, see how many colonies there are. If there's too many, do another dilution, and keep doing dilutions until you get to a number that has between 30 to 300 on it. In SQA exams, however, you're usually going to get a plate that has under 10 on it, or you will be told the number specifically on it rather than have to count it yourself. So this, working backwards from a plate with a particular number of colonies to how many colonies you would have started with, can be quite complicated. So I do apologize if I'm talking through this quite slowly. But what we need to do is we need to look at each step in the process. So what we have is we had 10 centimeters cubed because we've taken one out of it. And in that 1 centimeter cubed, we have 5 colonies. Now this is 1/10 of what we had. So if we were going backwards into how many colonies we would have had in 10 centimeters cubed, it would have been 50. So we know we had 50 in here. What we did was we took 1 centimeter cubed and we diluted it by 10. So if we're going backwards, we did a 10 times dilution, which made it 10 times smaller. When we're going backwards, that means we would have to multiply it by 10, which means there would have been 500 colonies in this tube. Backwards again, we did a 10 times dilution, And again, we would have to multiply by 10. And that would tell us that there was 5,000 colonies in this tube. Now, this is where it gets a little bit annoying. Our original sample is what introduced all the colonies into our first test tube. The number of colonies introduced into our test tube was 5,000 because that's the number that we've worked out there were. All of these came from our original sample, which means our original sample must also have had 5,000 colonies. So 5 in the growth medium on the agar plate. Scale that up to how many there would have been in the first tube, multiplying by 10, gives us 50. Each dilution was a dilution times 10. So when we go to the next test tube, we need to multiply by 10, which gives us 500. Next test tube, again, a 10 times dilution, so we must multiply by 10. There was 5,000 in our first test tube. All 5,000 came from our original sample, so there was 5,000 in our original sample. We got another example here. Again, 5 colonies. That is 1 centimetre cubed out of what was 10. So when we're working backwards, we need to multiply by 10. So in that first test tube on the right, there would have been 50 colonies. Every single one of these dilutions that has happened has been a 1 into 9, which means a 10 times dilution. So every time we're going back to a test tube, we'll be multiplying by 10. And this is where we start using scientific notation. In this first test tube, on the left, we've multiplied 5 by 10 5 times, so it's 5 times 10 to the 5. Remember, in our original sample, that is what introduced all the colonies into our first test tube on the left. So 5 times 10 to the 5 is the number in our original sample. So how many in the original sample? 5 times. Here is one for you to try. This time we are starting with 3. So pause the video and have a go at this question. Hopefully you've had a try. In this one, we would need to multiply by 10 here to get into how many were in our 10 centimeters cubed rather than 1. Times 10 here, times 10 here, times 10 here, and that would tell us that we have 3 times 10 to the 4 in here, which is going to have all come from our original sample. 3 times 10 to the 4 is our answer. There are things you need to be careful though. While it is usually 1 centimeter cubed being diluted into 9 centimeters cubed to make a total of 10, in which case it's a 10 times dilutions, sometimes you will see the volumes that have been added are 0.1 centimeter cubed. If that's from a 10 centimeter cubed solution, then that is 100 times dilutions. If it is 0.1 from a 100 centimeter cubed solution, that is 1,000 times dilution. Also, one thing to be cautious of is that sometimes whenever you're working backwards, you're not going into how much was in the solution that was being added into a test tube, you're going back into a test tube, in which case you might need to do a multiplication. So here is an example question here. I'll give you time to do that. So pause the video, have a go at this. In this one, you have been told the number. Okay, hopefully you've had a go. What we're looking for is 1.19 times 10 to the 7. Now, what we had was 119 to start with. This is 0.1. And it was in 10 centimeters cubed. So whenever we're going back here, we need to multiply by 100. So that's going to be 2 zeros. All of these dilutions were 1 into 9. So that's a times 10, that's a times 10, that's a times 10. So I'm going to add on a 0 for every times 10. And then that's going to give us how much was in this solution. Everything in this solution came from that 1 centimeter cubed. So that is our final answer. And if we look at it, it's 1, 2, 3, 4, 5, 6, 7. 1.19 times 10 to the 7. I've got another question here for you to look at. Again, pause the video and have a go at the question. So hopefully you've had a chance at this one. To this one was 8 times 10 to the 8. Now what makes this question more difficult is that you are told that there was 100 centimeters cubed in here. Okay, so you're not going back to how much was added here. You want to know how much is in this solution here. That's where you're going back to. So we started with 80 colonies. We took 0.1 and 9.9. So 0.1 out of 10 is 100 times dilution. Again, 0.1, so going this way is times 100. This one we took 0.1 out of 10, so again, that's another times 100. And that's taking us to here. Now here we took 0.1 out of 100, and that is times 1,000. So 1, 2, 3, 4, 5, 6, 7, 8. 8.0 times 10 to the 8. So that is a tricky one. And we've got a final question here. Use the information to show that more than 10 to the 10 viable cells were present. Now in this question, this is from a very old past paper. You can go from any of these plates that you want. You can go from any of them. I'm going to go from plate C because plate C is the one that has between 30 and 300. So we had 60. 0.1 out of 10 was used. So going backwards, 0.1 out of 10 is times 100. 2 zeros. In this one, this is 1 out of 10, so that's a times 10, and every one of these dilutions that's 1 is times 10. So those two, another 2 zeros. This one here was 0.1. So 0.1 is going to be times 100. And then our final one here is 0.1 out of 100. So that is times 1,000. So when we go back, we have got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 6 times 10 to the 10, which is more than 10 to the 10. If you had done B or D as your colonies, B would have given you 5.97 times 10 to the 10, and D would have given you 3 times 10 to the 10, which again, all of those options are all above 10 to the 10. So I know this video is quite long. There have been quite a few examples as part of the video, but dilution is something that does come up, and there are calculations which are tricky, but are logical. So please, if you have any questions or you want any more practices, just come and ask.